Okay, so this is where we actually left in the last lecture. So we were discussing about how to create processes and then fork and how basically it is used. So just let me quickly run over one example here. Yeah, this is a program which actually shows you how to create a process, child process within main process, the parent process. So for the child process, we are using fork command, and this basically returns two process IDs, zero for the child itself and positive number for the parent process. So if you could see here, now once this is called, basically this splits your program into two parts. So there are not splitting, it's basically copying. So from here onward, your parent and the child process would start executing the same address space. So based on the PID, we would be actually differentiating what part of the code each process, the child process and the parent process would be executing. So because for the parent, let me just, I have one more. Okay, so I think this will work, no problem. So this particular part would be running on child process, and because this is a if statement, so the child process would be executing because the PID for the child process is 0, and the parent process is having the same code, but it will be running this part because the PID for the parent process is greater than 0. So when a child would be executing, it will add 15 to the current value, whereas on the parent process it will wait for the child to terminate, and then it will actually execute, and accordingly it will print the value for here. So this is how basically would be executing different programs. Now we can see, now this is Vim editor. Let's run this program and run. So the parent value is still 5 because it is not reflected back to the parent from the child, whereas the child value is 15. 5 plus 15 would become 20, but for the parent the value is equals to still 5. So this is how we actually differentiate between the two. Now you have to give me a clue on what would be the expected output of this particular program. If you look at you have created a program in which there are 3 forks. So how many child processes would be created out of this particular program? So just forget this particular thing for now. And if in a program we have 3 forks, how many child would be created by this program? Any answer to it? So basically 7 would be child and 1 would be the parent. So in total 8 processes would be there, including the parent process, but 3 forks would create 7 child. That has to be very, very clear here, because one program is this whole program, which is a parent program. This would create one child process. This will create further 2 child process, and this will create 4 child processes. Why? After this would be called by 2 processes, and this would be called by 4 processes basically. So because this would create 2, this would be creating 1. So and 1 parent process, so this would be called by 4 processes. So in total there would be 7 child processes. Those would be created by this particular program. Now let me run this code, and then we see what exactly it means. This program which I'm showing here, this part is basically to return the process ID of the which is running and its parent process ID. So there are 2 functions, get PID and get PPID. So used to return the process ID of the parent function. So this basically returns us that information, and we could see, for if they are still running, we could see their entry into the POC directory of your system. Okay, so moving forward is now we have discussed about that the fork creates the child process, and then based on that it creates different process IDs. So each process on your Unix system or Ubuntu system is identified by the process ID, and a process can create the child process, and the further the child processes can also create the further child processes to do the task, whereas the parent process would wait the child processes to terminate, because each would be having allocated task to be completed. Let us suppose if I say the task is to read the number of words from a given PDF file. So it is up to the parent process how it splits that PDF file to different child processes. Each child process would count the number of words in its given number of pages to it, and then return the result to the main or the parent process, where the parent process would actually aggregate all the results from different child processes to get the final count of the number of the words. So it depends how the split is done. Now this is more programming part, how you want to split your data and how you want to collect that data. This is kind of splitting or parallelism you want to create. Now one question is like, do you think that on a single process, on a single core processor with the child and the concept of parent and child processes, are we still doing concurrency, or this is going to be parallelism? If a parent process can create a number of child processes, but we are still running on a single core processor, do you think it's still the concurrency concept running, or do you think the parallelism has started? What is your response to it? Is if I reiterate, like so it's still a concurrency concept, because the processes are created, but we have single code to execute a particular, we have only single code to execute the process. So it may be the child process and the parent process. They are just processes, so they would be handled similarly. Now this is what is happening in the main memory. So the processes would go to different state, whether it is a child process or a parent process. They have to follow the same cycle of the state of different processes. Now they would be in a ready queue, then running, then waiting, then interrupt, then running, ready. So that the same thing would be happening, and the parent process would wait the child processes actually terminate or completed. So that would be the state of the parent would always be waiting till its child are running, and the child would run in a similar fashion with the cycle which we have already discussed. So same states would be there. So each process, whether it is creating 10 child or one child, it depends. So let us suppose process P would create C1 plus C2. So now let me abbreviate it like P2 and P3. So these are also the processes. So now process could share the resources and the address space of the P1. Whenever process is created, it basically shares the address space and everything. Then after its loading, it could actually remove the previous content and load a new program, and it would become a new program then thereafter. So this could ask the operating system for new resources, or maybe using all the resources which are only allocated to P1. This depends upon the operating system to operating system how they want to see, but the threads basically use the same resources which are allocated to P1, that we are going to discuss in the next chapter. So here the process P2 would also follow the same life cycle which P1 would be following, and P1 would be just waiting for P2 and P3 to terminate or execute to full. So once they execute to full, till that time P1 would be waiting, and it will aggregate and take action after they are done. Here we can see that the child process is basically loading its own part. So this command is used to load a new program or new part from this particular family. This particular function loads a new data onto the child process and run that part. So it's not exactly copying the previous program that we discussed here. This program, there is the fork is being called. So each child process is just copying what the parent process is having. So whatever parent process is running, so they are just copying that, because we are not changing any content. But here what we are doing is, whenever a child process is called, this function would actually load this part into its memory. And so the new program for this child process would be this ls command basically. So this is a listing command which would be executed by the child process. I hope a bit of it is clear. Now, whenever a process is basically now process, whether it is a child or it is a parent process, they complete their work, they basically terminate by calling this exit command. And so what happens, and how the parent process would get to know about that the child process is actually executed. So it basically returns a status of the child to the parent process, which is captured by or given to wait function, and wait function would actually create the PID of that process which has terminated. So a process could actually execute till the last statement, and then ask the operating system to delete it using exit system call. It returns the status data from child to the parent via wait, and the process resources are deallocated by the operating system. So whenever a process, so it basically and the operating system would actually deallocate whatever memory has been allocated to it. Now, parent process may terminate the execution of child process using a abort system call. There may be the child exceeded allocated resources, task assigned to the child is no longer required, and parent is exiting basically. So parent is also terminated, and the process operating system does not allow a child to continue if its parents terminate. So this situation is called cascading termination. So whenever a parent is exit or it's terminated, all children or grandchildren, so there will be, they would also be terminated based on that cascading termination. The termination is initiated by operating system, so this usually starts with it. Whenever a parent process may wait for the termination of child process using wait system call. So here is it is given with the status signal. So the wait is passed by status, and when the status becomes exit for a child, it get to know that okay, this particular child has terminated. So based on that, it basically takes the action. Now there are two scenarios, like what would happen if the parent, no parent is waiting for child. So child terminated its process, but there is no parent which is waiting for it. Now for that particular situation, a child process would become a zombie. So if now, how to handle that zombie part is basically parent has to invoke the wait function or wait system call, and when the wait system call is there, so zombie process can actually terminate finally. So it would not be, it would be a normal child process, would not be called a zombie basically. Now in this other situation, when the parent is terminated without invoking the wait, so it may be possible that the parent process has created a child and it terminates itself, or some other program terminates it, and in that case there would be no wait function which would be calling or which would be executed. So in that case, the child process would become an orphan. So for handling the orphan, Linux system basically uh, generates a periodically and wait function call, so which actually takes care of all such orphan child processes. So it comes under as we have discussed that system D is a child, the process number 0, which starts when you boot your Linux system. So it basically invokes periodically a wait function, which would actually takes care of all the orphan processes. So once now the situation is whenever a child terminates, it tell the parent process that it has terminated, and parent process and get to know through the wait statement, wait system call. And in case when there is no parent waiting, the process would become zombie. And if the parent terminated without invoking wait state, then the child process is called orphan. For handling the orphan processes, the operating system itself invokes the wait function, and which takes care of all the orphan processes. So let's do one example and then we see. Now this particular process program is depicting how your zombie process would be created. We will see to it because the life of zombie process would not be long, because it'll that zombie process would be only till when the parent process is not executing the wait function or wait system call. So when the wait system call is provoked or invoked by the parent process, the zombie process would actually be converted into a normal process. So there would not be any issue. Now, if we look here, so what we have done here is the PID is now creating a child process. It would return the process ID. So if it is less than 0, it means it's not created. If it is equal to 0, it means it's a child. So what we are doing is doing nothing, just calling and creating a process to turn into zombie. So how that can be done? So because here we have added a sleep function. So this sleep would sleep the parent process for 50 seconds, and it will basically enables for the wait to be invoked. So what would happen is this process would become into zombie, and its status would change into zombie. Let's see it how it would be done. Like, you can see the status of all the processes which are running. So I'm just selecting two. Okay, so this is the status of all the processes, rather than just, if I say the complete would actually be if you are able to see my screen. So complete FS statement would actually give this very information. So I just want to look at stat information of the processes, and I can also type in command. So it's basically showing me two things now: the state and the process. So here S is basically which are correct processes. So for this we can do PS, and then we can look at what is the status. So S is basically telling me the state code. So interruptible the sleep command, and Z is basically telling the zombie process. So terminated but not reaped by its parent, because the parent is might have not initiated, or it's just doing nothing. So for that process, we will see a Z state for that particular process. So now let's run zombie and A out. Okay, so I have to do this SSH. Sorry for time. Okay, so PSEO, and then we want to see two. Am I typing? Okay, so here we can see that there is one zombie process A out which is running. So it will just be there. The state would be for just for 50 seconds till the time your parent process does not start its execution. So for that time, this process is called a zombie process. I hope. Okay, now moving next. Now, when we have multiple processes, so some application actually require and are designed to be like that. So they are multi-threaded, or we can say multi-processes. So Chrome browser is one example, which is multi-process architecture nowadays, because we have more multi-core system. So it is requirement to develop the application which are multi-processor or multi-threaded application, because there are more than one core available. So we have to utilize that feature of the hardware, and those applications that are needed to be developed like a multi-processor or multi-threaded application. So Chrome browser is one of the example for multi-processor, where more than one process is executed to run different parts of the total Chrome browser. So browser manages the user interface. So when you double click on Chrome browser, it initiates your one process, and the browser manages user interface, disk, and internet and network IO. Whereas for each tab that you open, those are handled by renderer process. And so number of tabs you open, so basically you are creating more number of creating number of renderer processes. So each run in a sandbox, so restricting disk and network IO and minimize the effect of security exploits. So each has its own sandbox to run, so that's why they are more secure to actually run, but still there are loopholes by which your Chrome browser can be attacked. So I know most of the web developers, they use Firefox, and they are also used for compatibility checking with the Chrome browser also. So most of the users would be using Firefox because it's more secure, and in comparison to different browsers. Anyways, coming back here is this is how the render process would be created for each and every tab. So if one tab crash, that does not crash the whole browser. Earlier, your browsers would actually crash whenever your one of the tab crashes. So this is not a case for Chrome browser, because it initiates a renderer process for each and every tab. Whereas if you have added plugin, so those would be independent different processes. So each would be running as a separate process for single application. So such applications are multi-processor architecture application. So now we have discussed that the processes are created. One process can create a different other processes. Now these processes has to communicate with each other. So how they can communicate with each other is basically depends upon what type of communication medium you want to set up. So there are two mediums that are available. One is called shared memory, and other is called message passing. We have discussed bit about it, but today we would see how they actually are implemented for particularly for shared memory model, how the different processes would be sharing information with each other. So over network system, I remember I discussed about that there would be a shared memory space where each process or each computer can actually access its data. So in that case, we actually discussed about one computer is connected to another computer, and here is third computer. So what they were doing, each was having a different the processor or cores, and this is processor P1, P2, and P3. So let's make it mu p, and mu p, so like that. So these are different processors, and they to a common bus to a different storage, which is basically your secondary storage, which are basically taken and shared by each and every processor. Now this processor could be an independent computer. So if I say computer, it means it has everything independent. Its RAM is independent, its cache is independent, and its are independent. So these are independent computers. So they are sharing a different secondary storage. So this is basically we can say some kind of a clustered system. Now coming to the granularity of, if we go to a level of process, then processes would also require the information to be shared, because what is a process? It's an set of instructions, and those set of instructions require the data to be executed on. So if we are performing A plus B, then we need to know, or your program need to know what is in A and what is in B. So whether this is an integer or it is a string, what exactly. So all that information should be shared. Now let us suppose A is held by process P1 and B is held by process P3. Now if some process has to perform this, it has to take the information from P1 and P3. So the communication has to be done now. So I mean to say that processes cannot run in independent. So they are basically, they need to share the information by cooperating with other processes. So cooperating process can affect or can be affected by other processes, including sharing data. So why do we need uh, the cooperation is basically information sharing, and then computation speed. If we split a process P into different processes, then the computation speed would always be better. In a single core architecture, P1, P2, and P3, they would be running on a same machine, on a same computing or in the core. So do you think that if we split our part into P1, P2, P3, that increases? Certainly. For example, let us suppose your process P has some component which wait for IO to be happening. So in that case, if we split that IO component to a different child process, then in that case, the child process, single child process would just be waiting while other part can't, keep on executing. So in that case, our whole program or the process is not waiting for IO to happen, but just sub-component or some child process of that process would be waiting for that IO to happen. So in that case, obviously the execution speed would be better. So that's why we create multiple processes. And it is more like, because nowadays we have multi-core system. Now processes or threads, they can actually run independently and in parallel because we have more cores. So on a single process, if you have core 1, CPU 0 and CPU 1, so this could actually run P1, this could actually run P2, this could actually run P3, and this could actually run P4. So we considering that P3, P2, and P4 are the child processes of P1. So it may be possible depending upon the basically the dependency of each process onto other process, but still it is possible that they can actually run in parallel in case we have more cores available in your computer, and which is a reality right now. Modularity, if you create uh, you know more child processes, it would actually give more modular approach of designing your program, so that okay, this part would be done by this particular child process, and your program would be much more modular, and it will give you the convenience as a developer, like you have to create, debug the program, which would be much more easier for you. So for cooperating processes, we need inter-process communication. Now there are two models and methods available. One is shared memory model and other is message passing model. Okay, so when we talk about shared memory model, in that case, a shared memory has to be created where and then attached to the address space of the process. Okay, so this is basically the memory. Now a region has to be created. First, the region is to be created, that this memory would be working as a shared memory, and then the processes would be given authority to actually use that particular shared memory. Now, normally in your operating system, we say that if some piece of memory is used by one process, it is basically constrained to be used by another process. In this case, when it is a shared memory, we have to get rid of that particular restriction, and it happens between the processes. So process P and process B agree to use this shared memory region, but they have to follow certain rules of synchronization, that there are different models. If you remember, we discussed about read after read, read after write, and write after read there are certain dependency things for synchronization of different memory models. So we are not discussing this right now, but the only thing is, so whenever a process wants to uh, create a shared memory region, it will first create this and then would attach it to the memory address space, its address space, and then it is shared by different processes. So it will actually give the pointer to, or pass the pointer to that particular region, and other processes can actually read from that particular region. So this is what is happening in shared memory model. We will get back to it. And now here we have message passing, in that the two processes are just they have to share some information and they are sending text messages to each other. So if I say, okay, so if I say in case of processes in the shared memory model, the size of the information that could be shared between two processes could be large, because we know that there is a space already. Then the memory sharing or the size of the data could be large. Whereas when we are doing message passing, so in message passing we have a buffer, and that buffer is used to just communicate the message from one process to another process, so two processes as a message queue through a buffer, and that buffer keeps on filling. So it may be zero length, it may be finite length, it may be infinite length of the messaging. So let us take an analogy of like you and your friend want to exchange a book. How would you do it? Like, one system is, because you are two processes, so you would start try to create a link or to find a region where you can place, one can place the book and other can actually take. So let's suppose you have a window, one, your friend would put the book there and you would take the book from that particular window, and that window would be working as a shared memory. So analogy to this particular thing is just your Twitter message. So if you have to send some information which is constrained to 140 words, so you have to write multiple messages to share a long information chunk. So you keep on sending messages and the other person would keep on receiving it, and this message queue is basically handled on Twitter cloud. So this is how basically you are sharing information. The same kind of thing is happening for the processes which are sharing information through messages, and this message passing is better, faster to implement, but the only thing is the size of the message. We cannot send a large amount of data through message passing. So both models are very successful. Each one has different advantages. So both are basically used in the communication between the processes on a same computer or between the processes on a different computer. So if you take example of client server model, so that is also possible for you. Now for this particular communication, we have a paradigm of, for shared memory model, we have a paradigm of producer and the consumer process. So producer would actually produce the information, and then the consumer would actually take that information from the process. If I talk about an area of the shared memory among the processes that wish to communicate, one process, the producer would create the information and put into the shared area, and then the consumer would take the information from that particular area. Okay. The major issue here is that the user process to synchronize their action when they are accessing the shared memory. So this would be handled in chapter number 5, that we would discuss how the synchronization would happen. The communication is under the control of the users, not the operating system. So how the communication would actually be happening, it is up to the developer of the program that how he or she wants to actually perform the communication to be happening. We have two approaches. One is called a bounded buffer. One is called bounded buffers, where we assume that it is a fixed size buffer of sharing, and then we could have practically no limit size of the buffer for this particular problem. And so the size is unbounded, but we would be talking about a shared memory information where we will be giving the size of that particular region. Next is in message passing system. So in message passing system, so we have a mechanism to basically share the information between different processes. So how that happens, there are two operations, those are provided. One is called send message and other is called receive message. Now in send message, we basically send the message, and this could be something like send message to process A and receive message from process B. So this is one kind of information sharing that could happen. Okay, so now here we have a paradigm for the sharing of the information. So we discuss about it, that unbounded buffer and the bounded buffer. So in there is no practical size of the buffer. Consumer may have to wait for like whenever a new packet is available. Then we have a bounded buffer. In bounded buffer, there's a fixed size, and consumer has to wait if it is empty, and producer has to wait if it is full. So basically, the region depends upon the type of the region that we are using for our information sharing. Now, there is an example for it. So basically, a circular buffer could be used for shared memory model. So here we can see that the buffer size is 10, and then we have one variable that is just keeping track of the input of the buffer, and the output would be just looking at what we want to take out of it. So circular buffer is basically with two pointers. One is for inputting, where your consumer is inputting the information, and out is for your input pointer is for your producer, and output pointer is for the consumer. So let's just look at so in this, basically the item is produced and your input, this would be placed in your pointer, so which is the next produced information. So this part is basically your producer part, and then we have, this is your consumer part, where it is looking at out buffer size. So mind it, for circular buffers, the size would be equal to n minus 1. So because we have, if your in and out pointer both are same, so we consider that it is basically an empty circular buffer. So I think you have done that in your other courses about circular buffers. So it's not of that particular value. We will go into detail of how your message passing would be done actually on Linux. Moving toward the next thing is message passing. In message passing, we use to send the message and then receive the message. The message could be of fixed and variable type. Now, implementing the variable size message are complex, but it makes a programmer life easier, because a programmer does not have a constraint to fix the amount of information that it can share over through the message. So one example of fixed size is your Twitter message, where you actually just has a certain number of characters those you can send. Now, if the process P and Q wants to communicate with each other, they need to establish a link, and for the link to be established, there is a mechanism which is automatically done. Then we have two different type of it's going back. Okay, so then we have two types of communication. One is called direct communication, and another is called indirect communication. In direct communication, we actually give the process. We pass in the name of the process to which your message should be sent. So send P a message Q, and then receive a message from process Q. So send and receive two function implementation is done. So whenever somebody wants to send information from one process to another process, the links would be established automatically. So that's process to process communication. It may be within your system, or it may be on a system on a different machine, but the links would be created based on the type of protocol you are using. So a link for the direct communication, a single link would be associated with the two pairs, one pair of the communicating processes, those two processes, and between each pair there exists one particular link for the information. Now, this is called symmetric addressing, where both receiver and the sender must have the names in order to communicate. Another variant of this is asymmetric, where the sender knows that which process it wants to send in, where the receiver just receive the message from any process. So basically that is kind of asymmetric addressing. Now for indirect, so we have okay, we have indirect communication. So in indirect communication we use ports, or called mailboxes. Now you know that we are interacting with your Ubuntu virtual machine through a defined port. So basically SSH is a process that runs and it listens to the incoming request at port number 22 normally by default. But right now here we have changed that to 2222. So you can see, so from here, from this part, from your host operating system, you are connecting using port 2222, and then you are passing the username as you want to connect, and then you are giving the basically giving the IP address or the domain name of your VirtualBox machine. So this is how you are using. Now most important is this port. Now port is called a mailbox. The messages are directed and received from the mailbox, and each mailbox has a unique ID. So in Linux, they are basically integers or numbers which are given, and processes communicate only through the shared mailbox or port. So there are different now processes and operating system can create a mailbox. So it can create a port. It sends and receives the message through that particular mailbox or port, and once the purpose is solved, so it basically destroy that mailbox or port. So the primitive for this is send a message. So send a message to mailbox A rather than typing the process ID, process name, and then receive a message from mail or mailbox this or port number this. So rather than giving rather than taking from, let us suppose this is a window, what we were talking about, process P1 and process P2, they basically take information through this particular shared mailbox. So that is given a port 2222. So you are trying to log in into a process called SSHD. So you are sharing a mailbox number 2222. So you send your host terminal would send information to this port, and this process is listening to this particular port and take the information, receive the message, and accordingly push back the result for that particular request. This is something a process created mailbox. Now it could be possible that your operating system creates the port. So whenever a port is created by your operating system, so it'll basically allow a particular process and can give that port to different processes also. So that is also possible, not binding a particular port to a process, but it is owned by the operating system. So operating system is authorized to allocate a particular port to other processes. So once it is created, it may be destroyed. It may be destroyed by your operating system, but within that time, it can also be allocated to the to different processes. So what happens is, in using indirect communication, we could use our multiple processes can share the same mailbox. So if there are two, three terminals you want to open. So you have opened one terminal, you do SSH1, and you open another terminal that would also use the same port for the communication. So it is possible that more than one process can execute the same port. Whereas in direct communication, two processes can actually share a single link, but in port or mailboxes, multiple processes can share the same thing. So let us suppose P1 sends information, P2 and P3 can receive it. But who gets the message, P2 or P3 or both? It depends upon the mechanism of doing. So it may be possible that we select on randomly basis that P2 would receive a message rather than P3, or P3 would receive the message rather than P2. That is also part of scheduling. So for that, this is also possible. Like all of you who are working for web development, then they know that either your Apache server, when you make it up, it runs on port 80. So port 80 is basically allocates you that Apache server is listening on this particular port, although you can always change those ports. So when you are actually doing the server implementation or administrating the servers, so in that case you would like to change these default ports. So basically every port below 1024 is called well-known port. So they are well-known ports. So every program that you normally install on your server, they would have certain ports to listen, and some are having a default ports for this. Like your SSH would be running on 2222, and then your web server would always be running at 80 port. So you can always change those default ports to be listened, because this is just a number, and we can ask the server process to listen on a different port for execution. Okay, now when there are different processes, those are communicating, we need synchronization. And for synchronization, there are some methods those are used. Message passing may either be blocking and non-blocking. In blocking case, when a process sends the information, it is blocked until the message is received. So this is called blocking send. And blocking receive is the receiver is blocked until a message is available. So it will just wait for the sender to send the information to keep doing its to do the next job. So it will just wait there and blocked. Non-blocking are basically asynchronous. In the non-blocking thing, the sender sends the message and keep continuing the work. And in non-blocking receive, the receiver receives either a valid message or a null message. So it's keep on looking at whether it has received or not, just run a subroutine and keep doing its work. So basically non-blocking and blocking, send and receive, are two methods of synchronization. There are different combination of it is available. Let us suppose we have a blocking send and non-blocking receive, or we have blocking receive or non-blocking send. So it depends upon the type of the synchronization we want on our system. If both send and receive are blocking, then we have a env. So this basically is a term that is used when we have both send and receive as blocking. So this is an example of how the blocking is basically working. So while the next producer is a message which is produced, so while it is true, so it just send the information till it is being acknowledged by your receiver end, and then receiver would actually receive the message, and then based on that it continue to work on other part uh, of the program. So this is just kind of very short example. Now buffering, so whenever we send the information, we need buffer. So there are three types of buffers those are available. One is called a zero capacity buffer, another is called a bounded capacity buffer. So in bounded, we have a finite length of messages. So sender must wait if the link is full, if the buffer is full. Unbounded is infinite length, and sender never waits for the information or the message to be sent. So now moving toward the example for how the shared memory is happening between two processes, P1 and its child process P2. So for that, we will try to run a program and then see how this would be actually happening. I shared two, three files with you on my learning space, so you can always look at there. So that is basically implementing this shared memory segment for between two processes. So one process would create a shared memory, put the content over there, then the other process would actually be reading from that particular process. So the process first create a shared memory segment. So here is a declaration or creation of a shared memory region. So once it is done, this would create a 0 byte region size of the region, and then this command is used to create the actual size of that region. So we expand it to 4096 bytes, and we want that shared memory region should be of this size. This is just passing you the address of that particular region. So here we actually allocate how much memory is for that particular region, and then we actually add in our this particular region into our address space using mmap, so that we would be seeing shortly. And for the process, basically we are using sprint to write into the shared memory space. So let's look at that particular program. So now here are two programs. One is producer and the other is consumer. For producer, let's look at the code, try to understand it. Let me do this in Vim. So here the process is basically what it is doing. It is giving the name to that particular shared memory space file system. So it's basically a file name. So it would be actually creating a file under dav /shm. So that's the file system or file location or the folder location where this file would be actually created. So we will shortly see to it. And then we have size of what size we want to create for. And then we are creating basically some messages that we will be putting onto that particular shared memory space. So this is the file descriptor used by which would be handling the location where your memory segment or region has been created. And further we are using base as a pointer. So there are two pointers that we are using to point to different region or also within that particular file. We will see to it. So if this particular says if it returns your shm_fd is equal to -1, so the shared memory creation is failed. Now once the region is created, then we actually give the size. So we configure the size of the shared memory segment using a ftruncate function. And then here we are basically using mmap function to attach the shared memory segment that we just created into sh_fd into the memory address of the process. So mmap is used for that. And here this map shared is basically telling that okay, so this would be actually visible to whatever changes we are doing. This will be visible to each and every process that is sharing this particular space. So here is basically in this process. So once this is created, another function is display, which is basically displaying the number of 64 number of bytes from this particular location. Now what I'm doing is I got this into a pointer information, the address of that particular file system, and then keep on pushing my data into that file system. So I use sprint and I'm sending the messages, message 0, message 1, message 2, and then message end. So I send everything, and basically I'm just trying to display what are the content for that particular location. And once done, we will close this particular program. So let's see how try to run this. Now for this, I have a makefile created, so you can use this makefile. Let me see at what is in makefile. Okay, so let's do makefile all, and nothing to be done for all. So it's already done. So here I have cons and producers. So let's run. So what it will do is it will display the producer before we actually added anything. Like here you can see before we actually added, we are displaying the contents of the memory location. Here you could see there was no data available. Now once we added the information into that particular file system, here we again call this function to see the location. Now you can see some data is already there. So we can actually run this again to see the information. So here you could see now because the object is already created, and we see the same thing again, and then we overwriting into it. So this second call is basically just to see, to distinguish, like here there was no memory file system that was existing, and here we can see it was already existing. Now we can actually ls into dev, then shm, and here you can see this particular example is already there. So we can always care into it and then see the contents, what contents it has. So you can see we have written study operating system is fun. So this file is now capturing that information which we have already written. Now moving toward the producer example, sorry, the consumer part. So what consumer is doing here is it is basically initiating based on the name, which file or name it wants to see from the shared location, from the shared region, and then it opens that into a read-only format. So here you can see this opens that particular file in read-only mode. This is basically giving the file permissions. Those are for that particular file system. So these are the file permissions. 0666 is the file permissions used by this function. So it is just reading. Now we created an object, we attached that object to the address space of the process, and then we are just displaying the contents of that particular memory location. And once done, we are going to unlink that. So it is going to delete and remove that shared memory segment. So once the consumer produces, it places a file into the shared and that has some contents, and once the consumer reads that, it will actually remove that information from that location. So let's run it and let's see what it actually throws. So it's basically telling us, okay, this is what is written there. So it read that and post onto the screen, and now we can check whether that location is existing anymore or no. So we cannot find that file. So it means that it has been already removed by the other process. So one producer produced some information, put into some place, and your reader or the consumer process actually took the information from there and then read it. So this could happen here. We have used in two different files, so this could happen within the same file also. So where one process is actually creating the information and the others are just using that particular information for their purpose, and then just delete that information. So I hope it's a bit clear to you that how that information sharing is happening. Parent process is writing something into the shared memory, and then your child process is reading from that shared memory. So the functions those are used are pretty much same. So here you give the name of that shared memory file system, and then you create that object using this name. So here name is the name of that file system, and here you put in the attributes, like it is your producer. It will have one more thing. It will have o underscore create or o underscore read only. So basically we are just reading from here. So we opened that particular region as this particular mode. So that would be giving address into the pointer. And now this pointer has to be attached to the memory region. So the memory region here is basically the memory region, I mean to say the address space of the process. Now you should be very clear on one is the memory region, like which is a separate memory location, and then you have the address space. Now address space is the process space where your process instructions are already executing. So you are attaching that particular address space, your shared memory segment, to your address space for your program to actually execute from that particular part. So SHM base would actually return the pointer to that particular location, and then it is basically reading from that information. So printf whatever is in the SHM base, it will read that file content and post onto your terminal. Once you are done, you will actually remove that shared memory segment and can continue working on your stuff. Okay, so moving forward, next is the socket. So socket is basically defined as an endpoint for communication. Here, if you remember, we actually write some processes like this, where this is an IP address of your system or the computer system, and this is the port number of the process. So socket is one step ahead, where we are using this for communication between a client server model. So a client has its IP address along with the port number, the process ID, the mailbox for that process, and the server has the IP address and it knows that which port and mailbox it is listening to. So the port, is a mailbox of a process, and this is the IP address. So socket is basically, now this complete is called a socket. So the combination of the IP address as well as the process ID make it a socket, which becomes an endpoint for communication between two processes. Concatenation of IP address and port, which include the start of the message packet to differentiate the network services on host. So if you are doing 61.25.90.8.22, so what does it mean? So basically you want to access a service given by your SSHD process, and if you are doing this, it means you are trying to access the services those are basically offered by your Apache web server. So communication consists between a pair of sockets. So whenever this communication happens, so there are two pairs of sockets, those are there. So all well-known ports below this are well known, and you can always assign something higher than this for your customized port numbers. And the UWF is basically used for looking at your terminal, the ports which are open and other information on your Linux system. There is a special IP address that is 127.0.0.1. This is called loopback address, or we also call this as localhost. So as you know that we are using this for SSH to your what I call the virtual box. So what we are giving is something like this, 2222. So this is basically the socket which knows that I have to hit this particular IP address on a network, and on that particular process I have this process 2222 which is listening to the request. So our terminal is sending information to that particular port, and the receiver, which is your Ubuntu machine, is listening to your request and then responding back to it. So here is one example. So this is how your communication would take place. So socket communication would happen like this. Pipe is basically is a process or the function which is used by the parent and the child process. So it is within a program process. So once a parent process creates a child, they can use pipe as a communication media. Okay, we have an ordinary pipe allow communication in a standard producer consumer style. So producer produce the information and the consumer consumes it through the read pipe. So basically it is just like you can say a two type array. So it has two element array. So one is the read end, another is the write end. I'll take you through one example program. The pipes are unidirectional because that's why we need two parts of it. So one is for writing and other is for reading, and they are unidirectional. A pipe of this much is created. We are basically, your parent process is writing into FD write end. Now FD write end is 1. So FD1, it writes into FD1 and then closes that part, and then it opens, your child process would read from the read end, which is FD0. So how that is happening basically, because your FD1 for the parent would become FD0 for your child. Okay, so the same information is basically transferring. So let's run this. Okay, so basically what we done here is we send information on FD write end, and that information has already been read by the child. So child read the message. Now what was the message? It was greeting. So it means that this communication is actually working. Now this happened on two processes. One is the parent process write into, and it is read by the child process.